In this module, we are going to play with the first law of motion due to Galileo. Okay, so if you remember, the first law says that in the absence of a net external force, an object will keep on moving at a state of constant velocity, and this, if you remember, can be arrived when f equal to 0. This implies that a has to be 0. Okay, this is the one law which I have not named yet, from which I told everything in this chapter will come out. Okay, and the first thing that comes out is the first law, and this happens when f equal to 0. Okay, now there are a couple of things you need to understand about this. Okay, the first is that you can understand that every body resists a change in the state of its motion. Okay, this seems like a mouthful, but what I'm trying to say is that if there is no cause, then you see that the change in velocity with time is 0, which means that a constant velocity is what the body tries to maintain. Okay, or it could be at rest. At rest velocity is 0. Okay, which is just a special constant. So if there is no force, then the body tries to be at rest or at uniform motion. Okay, so this property of a body to resist the change in state of motion, to resist acceleration, is called inertia. Okay, inertia. Now, inertia is not a word coined by Galileo. Okay, apparently, yeah, but still, he was the one who gave this idea. Okay, that every body has inertia. It has a tendency to resist the change in motion, and more the mass, more is this inertia. Okay, and this can be understood from this law. Okay, if I try to push an object, more the mass, if I keep an elephant, I can't draw an elephant. Okay, if I keep some very heavy mass, which is like say 1 ton or something, I know that it's harder for me to cause acceleration. Okay, so this property is what we call inertia. Very important to understand that. Okay, and there is a phrase which I don't prefer a lot, but which is, you will encounter it a lot of times. It's called inertia of rest, and sometimes you will hear about inertia of motion. Okay, these are common examples. Okay, this doesn't make a lot of sense because rest and motion are relative. Okay, and a body resists a change in its state of motion. In other words, it resists the change in velocity. Doesn't matter if that velocity is 0 or a constant. Okay, that doesn't influence its inertia, but still these terms are used for the two cases that are very commonly seen. One is, this talks about when we are trying to get a body starting from velocity 0 to some v, and this of motion talks about, the inertia of motion talks about when we are trying to stop something, when it's coming from some velocity to 0. Okay, so you have seen very famous examples like why you get a backward jerk when there's an acceleration in a car. You can understand this using the concept of inertia. Okay, I'll do this quickly, and examples like this should be easy for you to handle. If I am in a train or bus or something, I'm sitting in my chair, and suddenly pedal to the metal and acceleration starts. What happens? The bottom part of me will experience a force because of this chair, yeah, and that will be able to provide this acceleration for me. But the top part does not have an external force, and you know now that if there is no net external force, it will want to be at rest, whereas everything in the bottom is rushing forward. So I here will feel like, oops. Okay, I'll get a backward jerk. Okay, so similarly you get a forward jerk when a brake is applied. You can understand this, yeah, understand this as a case of this. Got it? Okay, so yeah, so And one more, the next important thing is that the next important thing is something that you might not have realized. What I'm talking about is that inertia, or the first law is a two-way street. What do I mean by that? What I mean is very simple. Again, you can understand this from f equal to ma itself, that we have been till now talking about if f equal to 0, then a has to be 0. But you know this is a two-way street. By that I mean even acceleration, if you have the information about acceleration, you can predict about the net external force. So if I tell you a is what is 0, then you can predict that the force, the net external force, yeah, there should be vector signs here, has to be 0. Okay, so net external force has to be 0 if the acceleration is 0. You got it? The net external force has to be 0 if the acceleration is 0. In other words, if you look at an object, that object is going at constant velocity or it is at rest, what can you tell about the net external force? That it has to be 0. Right? Okay, everything dandy. Now, pause for a second, close your eyes if you want to, get my bad handwriting out of your brain, and think about this. Have you ever in your life experienced a situation in which you see a body zooming past you, you see an object zooming past you, in other words, you see it getting accelerated, starting from rest and moving on its own, but there seems to be no external force on it. Okay, there seems to be nothing pushing it in that direction, but it's still going. Have you seen this experience? If you have seen this, have you had this experience rather? If you have had this experience, then Newton's law is not valid. And just because it's coming in exams and all, I'm teaching you it's not valid. Think about it for a second. Okay, if something is not stricken you, or you have not been, blessed with some enlightenment, it's not your fault. Because we are taught to sort of accept these laws. But yeah, think about this. If I am again sitting, we love to invoke trains in the study of motion. Okay, if I am sitting in a train, yeah, and I drop my, I don't know what, I drop some chips packet, or I can't draw chips packet, or something, a book or something that I was reading. Okay, I drop it. I am here somewhere on the berth. I'm not levitating. Okay, so I drop something on the table, on the train floor, and the train starts to accelerate. Train has a huge acceleration. Okay, now I am looking at this. What will I observe? You guys have seen this experience, haven't you had this experience that in a really, some your dad is really or your friend is really on road rage mode and driving really rashly and accelerating a lot, and you drop something, what happens? Does it stay with you? Does it belong to you anymore? Yeah, you know what I'm talking about. It zooms back, doesn't it? Now when you are looking at it, you are like, what is happening? There seems to be no external force on this. But it's still having an acceleration backwards. How is it possible? I just told you that you shouldn't have any acceleration if there is no force. Okay, so in other words, why did I tell you about this two-way street thing? Okay, because here I'm seeing that acceleration is non-zero. That means for me the force here should be non-zero. That is, for me, the first law doesn't seem to work, which does not augur well for a law. Isn't it so? Let's take another example. Okay, If there is a lift, suppose there's a lift. I'm standing inside that lift. Okay, and I have an apple with me. Yeah, Newton's tradition. I'll hold an apple. Something. Okay, I'm holding an apple, and what happens is that this thing, the cord that holds the lift, it breaks. Suddenly it breaks. Okay, what will I feel like, okay, when it's broken? You know, if you have, you know, taken a dive in a pool, or if you have seen any videos on the internet or something about people falling in free fall, you know that you will be, you know, floating around. Okay, you will feel weightless. If you look at the ball, what will it feel like? Or if you look at the apple, you will feel it's floating. You will feel it's floating. So what will you feel its acceleration to be? 0. So if I ask you what's the force, what will you say? Force is 0. Now I have your, you know, clever, trusty sidekick over here, who's firmly fixed to the ground. Okay. Now he looks at this, and I ask him how much is the acceleration of this ball. What will he say? For him, the acceleration is, g downwards. G downwards. For him, it's falling. So for him, the force is not 0. Oops. Some trouble is there. Both can't be right? Force can't be 0 and non-zero both at the same time. Who's right? $1,000,000 question. Who's right? Okay. So now I'm going to, you know, ease your burden a little bit and tell you this, that there are only some particular places where Newton's laws are right. Okay, and they are defined, those particular places, or we call them frames of reference. You would have heard about this, frames of reference, or particular observers who are allowed to apply Newton's laws, because only they can apply it correctly. Okay, and those frames are called, these frames which are allowed are called inertial frames. These are called inertial frames. Okay, and I know you would start to ask, if only some frames are allowed, why are we calling it law and all? Isn't it supposed to be a definition? It's a very deep question, okay, and I'll try to answer it a little bit. Okay, it is a definition, but why can we call it a law? I'll talk about that. Okay, so it's allowed, inertial frames are allowed to apply Newton's laws. And the first inertial frame, why Newton was allowed to, Newton was able to frame these, Galileo was able to frame these, is Earth. Okay, so when I'm standing on Earth, I'm not wearing like roller skates and zooming around. Okay, I'm just standing on the Earth. Then I look at a block. Okay, then I look at a block which seems to be at rest for me, or acceleration seems to be at 0, or it could be at constant velocity, it doesn't have acceleration. Okay, then I will think that the force is 0, and I'll be right. In my frame, if acceleration is 0, then force is 0. Okay, and I'll tell you a little bit more about this. If you look at this block, you learn later to do this formally, but right now I am sure you have an intuition for it, that the Earth, by later I mean just the next module, okay, not like later classes like some teachers keep telling. Okay, so yeah, the ground pushes you with some force upwards, and you know the Earth pulls you down. You know that we will not go into those forces nature just now. Okay, and you know that you see that this block is not going into the Earth or flying off, so you know that the force has to be 0 in the vertical direction as well. Okay, this I was talking about the horizontal direction. Yeah, so in the vertical direction the force has to be 0, you know that. But you know what, if I am very, very precise, if I grow a lot of white hair and become a very talented measurer of things, and I measure the force, the total force, I'll find it to be not 0. I'll find it to be I'll find that there is some small amount of force, even though this seems to be at rest. Okay, why is that? It's because Earth is not exactly an inertial frame. Okay, not perfectly an inertial frame, but for our purposes and till the level of observation that was there for a long time, Earth behaves like a very, very good inertial frame. Okay, so Newton's laws are valid from the Earth's frame of reference. That's why it's useful for us. Okay, and if you go to some deep space away from all gravity of all planets, and you throw a ball, and I talked about it in the last module also. If I throw a ball, okay, after that the velocity will remain constant. Okay, and the force will be 0. So this is also a inertial frame. Okay, but how can it jump from one inertial frame to another? How? Okay, the trick to this goes back to a study of relative motion in kinematics, where I'm sure you would have learned, otherwise I'll recap it for you, that if there are two observers at v1 and v2, okay, constant velocities, moving at constant velocities, okay, and they look at a third body, look at a third body, they look at the third body, both of them, if I ask, okay, whatever be its acceleration, whatever be its velocity, if I ask both of these guys, they will report the same acceleration a. Okay, as a guy, if I ask a third guy who is at rest, he'll also say that the same a is there for the body we are looking at. In other words, for constant bodies moving with constant velocity with respect to each other, the acceleration of a third object or an nth any other object has to be constant. Okay, so you would, I think you would have got where I am getting at. Okay, if I found one inertial frame, which is the ground, which is the earth, any other frame which is moving with constant velocity with respect to this frame is allowed to apply Newton's laws. The world will look the same in that frame, and all these frames are inertial frames, and you can happily apply Newton's laws over there. Okay, you got it? So why is this, yeah, to the all important question, why is this called a law? It's because it's valid in all inertial frames, and there are ways of extending it to non-inertial frames also, which we'll learn in a later module. Okay, so yeah, now you got the whole story of when the force is 0. Okay, so the next module we'll start talking about F equal to ma when force is not equal to 0. Okay, from where did we arrive at this expression is also something that is not left, that is still left to understand. That we'll talk about in the next module.